Hello, my name is Todd Rothman, and I want to welcome you back to Organic Chemistry 1. In this video, we're going to go over bond angles. Now, we just finished up with Lewis drawings, and one thing that we didn't do is identify the angle of the bonds in the molecules that we drew out, right? So we want to learn more about now its geometry and, like I said, the bond angle. So that's what we're going to do right now. This is a very short video, but it's a very important one nonetheless, but it's not too hard. This one chart will help us organize all of our thinking. Now, what does it mean when we talk about bond angles? Well, what we're referring to is what's known as the valence shell electron pair repulsion theory. Now, what this simply means is that electron pairs want to be as far apart as possible. And this is something that is independent of the atom. It really is just about electrons. So this is not a property that has to do with a specific atom. It just has to do with the number of electrons around an atom. So we could literally illustrate this in the following way. We could say that, let's say, for example, we have this atom, and we don't care what that is, carbon, nitrogen, oxygen, who cares? There's an atom. Now, if this atom has, let's say, two connections around it, then what we would do is we'd want the electrons of those bonds to be as far away as possible, so a straight line makes sense, right? So if I have two things, the best way to put those two things is 180 degrees apart. So this right here is 180 degrees. And that's because there's two things. And again, the goal is to get everything as far apart as possible. Get these electrons as far away as we can. So let's say we had three things, right? So we have an atom, and let's say it has a bond here, and where would be the best place for the other two bonds? Well, in this case, it would be 120, right? Regardless of what these atoms are, if I have three bonds, and that's it, nothing else, the best way to separate them from each other is 120 degrees apart. And that's the idea. By the way, this is called linear because it's a straight line. This is called planar, or also known as Trigonal Planar, but what it means is that it's flat and it's planar and everything is 120 apart. So we call this a planar molecule. By the way, planar, if you take a molecule and you put it up against a wall, if every single atom that's connected to that central atom, like so for example, this yellow atom in the middle, if we put it up against a wall and all three of its connections are touching the wall at the same time, that's planar. That's all it means. Non-planar is if one or more of these atoms are pushing out away from the wall, either behind or in front of the wall. Then it's non-planar. But in this case, it's planar. Now, this is all we're going to do. We're going to think about how many atoms or how many connections are around, how many coordinates are around an atom, and what's the best arrangement of those coordinates. But we're going to also learn now that lone pairs play a role, and we'll see how that works in just a moment. However, before I finish up, let me just emphasize, we don't really care about the type of bond. So, for example, if I have an atom and it has three things, and so we're going to do this right here, 1, 2, 3, like I just showed you, and it so happens to be that one of them is a double bond, it doesn't change anything. This atom is still, here's an atom, there's an atom, there's an atom. So this central atom here is still going to be planar, right? This is still 120 degrees. And by the way, that's in any of these angles here, all three of those angles. If you measure any two bonds, the distance between the two, it's going to be 120. This is planar, or trigonal planar. So it really doesn't matter the type of bond. What matters is the number of coordinates. That's what we're going to see here. So let's go up to the chart now that you got a little introduction to this. Okay, and by the way, it's maximize the distance between electron pairs. And by the way, bonds is included here, not just lone pairs. It could be two electrons in a bond. All we're doing is maximizing the distance of them. All right, so here's our little trend. If we have, let's say, no lone pairs and we have two coordinates around it, two bonding groups, then it's linear, like I just showed you. A straight line is the best way to separate everything away from each other, 180 degrees. Now, you might say, well, what's the difference between electron pair geometry and molecular geometry? I'll show you that in just a moment. what we really care about in our course is molecular geometry. Not so much electron geometry, but I like to be complete, so I show it to you here. So it's still linear because there is no lone pair. Electron geometry comes in when an atom has lone pair as well as coordinates around other atoms, okay? So we'll see that when we go down two more. So the next one is 0 lone pairs and 3 groups, and I just showed you it's called Trigonal Planar, regardless of whether it's the electron pair geometry or just molecular geometry, and it's 120 degrees. Now let's look at this next one. Here we have a lone pair and then we have 2 things around it. So let's draw that out. So imagine if I have an atom and it's got 2 things and a lone pair. So we have 2 things right here and there, 2 different atoms, and then a lone pair. Well, here's the thing. This lone pair takes up space. As a matter of fact, it takes up more space than if it was a bond to something. So this here is going to take up more space than if there was an atom connected to that. So lone pairs occupy more space, and what you'll see is it tends to bend things. It changes the angle a bit. But now this is our drawing. Now let's go back up for a moment and let's take a look at what this is saying. Here it says trigonal planar, right? It says planar. But here it says bent. Why? Well, here's the story. And by the way, I wrote around 120. You don't have to be precise here for this one. Here's the story. There are 2 ways to look at this. Consider it. One is whether you include the lone pair in your consideration of geometry. Normally you don't. Lone pairs are not usually considered when you deal with molecular geometry because all you really care about is the angle between the central atom and its 2 surrounding or as many surrounding atoms that it has. So from that point of view, if I ignore the electron, I put my hand there, then this is really just bent. Notice how it's got that shape of something that's bent like that? So that's why it's called bent. But if we do include the lone pair, if we wanted to include that lone pair in its geometry, then we would have to include that electron pair above, and that's what makes it planar. Now it would look similar to any of the above planars that I labeled here. So what we need to recognize is that traditionally in our textbook and in class, they're probably going to call this a bent geometry because they refer to it in its molecular geometry and not including lone pairs, atoms that don't have atoms with just electrons. We ignore the electrons in our consideration. Okay, now this is not exactly 120 because the lone pair is taking up more space, so it bends those bonds a little bit more than it would if it was not there. If it wasn't there, it'd be like 120, but it pushes it. So this angle over here between these 2 right here, it's not 120. Okay, it's actually a little less than 120, but for our purposes in our class, we're going to say 120, around 120. Okay, but the lone pair tends to push a little bit and change that angle. All right. So what if you have just 4 things? Well, I think you guys are familiar with this. This is classical for carbon, like methane, right? sp3 carbon. And so if you have just 4 different groups, the best way to orient them is not planar, is to put it in the 3-dimensional space. So if this is our atom, and we have 4 different things, it turns out that 2 of them will be on the plane. So if I take these 3 circles, these 3 atoms, whatever they are, carbon, nitrogen, oxygen, it doesn't matter what they are, right? That's the point. They would all touch the board or touch the wall at the same time. But when those touch the wall, the other 2 that are left will not. They will come out of against the wall or behind the wall. So, excuse me. So we will have one that's wedged. We draw it wedged. That means that it's coming away from this page. It's coming out towards you if you're looking at this from the page. And then another one is going to go behind the page, dotted. We use a dash bond, and that means that this is going behind the page. So if you took this molecule and you push it up against a wall, 2 of those atoms relative